All right, everyone. Next up, we have Martijn Visser, who is at Delta Res, and he'll tell us about how Julia is being used to build a strong foundation for geospatial innovation.
All right, my name is Martijn Visser. I'm a hydrologist by training, and I do a lot of data processing as well. And in this case, actually, so I'm doing a lot of Python. You even learned some Fortran, but a couple of years back in 2014, we had a project at work where we had to deal with large point clouds. And so basically, I wanted to do it in Python because it's nice and easy, and I didn't want to do it in Fortran. But in Python, quickly, it was clear that we would have to loop over individual points in a point cloud and do like custom processing on it. And this is not really the kind of use case where Python shines. And so here I'm just showing a simple function that shows basically what I like about using Julia, where basically I just put in an array of colors and I stuff in a point cloud, give it a function that converts each point in the point cloud to a pixel on the image. And by this short amount of code, I already have a function that can basically draw like a nice profile like this. In this case, I put in a function that colors the points according to their distance along the or into the profile to look at depth a little bit. Well, that was just point cloud processing, and I also wrote like a little library to read and write point clouds. But quickly after, I wanted to, like, of course, to write my results, which are often like geospatial rasters, away. And if you want to do this kind of thing, and there's quickly, you probably want to use GDAL for that. GDAL is from ArchGDAL. It's a C++ library with a C API. And basically, one of the things it solves is it basically goes one step away from the individual formats, like geospatial formats. Not just rasters, but also vectors. They usually, there's lots of different formats, and to illustrate that, I can perhaps. So this is from the documentation, some raster formats that are supported by GDAL. It's quite a list, and it's true when you receive data. Usually you prefer to have some standard like GeoTIFF, but very often you get some kind of format that you never even heard of. But more often than not, GDAL just has a driver for it. So that's why it's very convenient to be able to use GDAL. So we have the GDAL.jl library that lives under the JuliaGeo repository. Basically, what it does is based on clang.jl. So it's not the wrapper that I made, but it's the code that writes the wrapper. So when a new version of GDAL comes out, I can just regenerate the wrapper, and all the new functions that are in there will be automatically generated. And one of the other points about GDAL is that it's so especially at work, for instance, a lot of colleagues are using it from Python, but it has a bit of a bad reputation for being hard to install with the binary dependencies. And well, rather than going around to colleagues to help fix their GDAL installation, now I actually could use the binary builder to consistently build binaries across platforms, and fix that problem for everyone. And at the same time, Yixian, he's worked on the ArchGDAL package, and whereas GDAL is more or less a one-to-one mapping of GDAL to Julia, with some nicer things like error handling and stuff. ArchGDAL, it's more Julian take on it. It creates its own functions. It's making use of multiple dispatch, and being closer to what you actually want to use as a user. So basically, this for a typical geospatial workflow, like this is often your entry, because this is the data that you're getting, and you just want to pull out the data and do stuff with it. But once you do that, like for rasters, for instance, you can make use of Julia images, for instance. There's lots of amazing functionality there, the segmentation, or just the fact that that I really like that also in my previous example, where this is just a two-dimensional array of colors. So we can take that out of GDAL as well. And if you go on the vector side, then there's other stuff happening, like in Julia geometry. There are geometry types. That's more like the native Julia way of doing things, and we want to make it as easy as possible to go from this a GDAL wrapper to do your own thing in native Julia. And one thing that helps as well is the Geo interface that's also under JuliaGeo. But that basically it tries to make one thing. It's based on the Python Geo interface. It provides certain nice functions. So we have different pointers basically that represent the geometry. But we don't want to have to deal with the pointers, so we just want to make a plot, for instance. So in the Geo interface, there's plot recipe that you just say plot, and then it pulls out the geometries into Julia, and you can make your plot automatically. I'll show a short workflow. Since we're in England, probably a lot of you don't have the time to actually explore around and go around. So I just pulled in some open data, in this case from the Lake District. So some of the data that we have available is elevation based on LiDAR. So this is a 1 meter raster. And here is basically an ortho image that has pixels of 20 centimeters. So this is 10 by 10 kilometers, so that already means 50,000 by 50,000 pixels. So these are pretty large data sets. But if you load these into GDAL, you can easily extract a subset of it, or you can read individual blocks that easily fit into memory and do your processing on the go. So let's see if you can read this. So here I have a tiny little workflow sketched out. Basically, the idea is, so this is the map. And here's the Lake District. And so this is the area that I just showed. And so say, and the rasters that I have there in a local projection, the English standard. And so suppose somebody gives you some kind of polygon. Here we're just drawing it in GeoJSON, which basically gives you latitude, longitude coordinates and that make up polygon around a certain area. I already copy-pasted this into the code right here, the JSON string. So what we want to do now, we want to see for this polygon. Now we want to see the raster. So that means first thing is we have to project from the WGS 84 projection to the local British one. And we can do that with GDAL. So this is from ArchGDAL, the syntax that can be used for it. It's making use of do blocks a lot to like make use of finalizers to be able to free up the things that are allocated by GDAL. This is a safe way to use it. It does lead to quite a bit of indentation, but as you can see here, out comes a geom, and what it's showing here, you can see that the numbers change a lot. This is now in the local coordinates. So yeah, if you think this example is difficult, well, that's not right, because it's simple. And that just means that the geometry doesn't self-intersect. And so, whoops, let's get so this is the geotransform that basically indicates where the raster that we have is located. And these are some functions. Basically, yeah, I think they should probably go into the library somewhere, because what we want is to go from XY to raster indices. So from the geometry, from the polygon that we have, we want to get the bounding box. And this is also a GDAL struct. And now we have indices into the raster. So from 22,000 to 24,000 rows, those should contain that in this polygon that we have. So now let's see and try actually to just get that image out of there. And bloop. This is a nice thing about using Juno, because you can just directly see. This is the lake, the Red Thorn. This is, by the way, the third highest peak in England, the Hellefiend, I think. So what this returns is a permuted DIMS array of image stack, and it's quite a type. But so we can also just collect it, and then you'll get just a matrix of color. And so in this case, and just to play a little bit more, I am getting a hill shade, which is in Peter Covesi's perceptual color maps. There's a relief function, and this results in this kind of data. And what I just, one of the nice things, so here, you shouldn't take this too seriously, but like as a hydrologist, I was just playing around with a function that basically you start at a certain point and you find the lowest neighbor and you go in that direction. So you get like a local drainage direction. And so this function basically starts at a certain point and draws out this path for you. So you can use this to very easily develop cool functions based on geospatial data. Plenty more things to do. We want to make it easier to integrate with rasters with pure Julia functionality. For instance, axis arrays, we can just attach the X and Y axis, something to investigate. And well, we're not quite done yet with finishing converting to the 0.7, but we'll get onto that very soon. And well, thanks to Yishian, Fabian, Isaiah, and Elliot for a lot of things that I'm presenting. Any questions?
All right, is there any quick question? We're falling a little bit behind. All right. Well, please thank our speaker.